So what is solubility product? Solubility product, or KSP, is an equilibrium constant, and it only applies to salt that are not soluble. So for salt that are soluble, they will not have a KSP value. So KSP value typically is a small value because it quantifies the concentration of the cation and the anion that is present in the solution. So hence KSP, the K is an equilibrium constant, is only for salt that's insoluble, and it allows us to quantitatively analyze how soluble this salt is. S and P, the S represents the solubility of the salt, and P is actually the production of the concentration of the ions, and bear in mind the unit is actually a multiple of the unit of concentration. So let's quickly take a look at the one example. Let's take a look at lead 2 sulfate. So the first step to do is to write the dissolution of lead 2 sulfate in the presence of water, and this is the equation. And this will be the KSP expression, since for every 1 mole of lead 2 sulfate that dissolves, you get 1 mole of Pb2 plus and 1 mole of sulfate. And hence the unit of the KSP is mole squared dm minus 6. In the next example we look at is the silver carbonate. In the dissolution of 1 mole of silver carbonate, you get 2 moles of Ag2 plus and 1 mole of carbonate. Hence, this is actually the KSP expression, and the concentration of Ag plus is raised to the power 2, carbonate to the power 1, and therefore the unit of your KSP will be mole cube dm minus 9. The key thing to note when studying the solubility of an insoluble salt is that you can quantify the insolubility by 3 ways. Aside from quantifying solubility of silver carbonate by KSP, which is this value, we could also quantify the solubility of silver carbonate by the number of mole that can dissolve in per dm cube of water, or by the number of grams that it can dissolve in per dm cube of water. And it's important to take note when you compare the solubility of 2 different salts. You can either compare them by gram per dm cube, mole per dm cube, or KSP. If you're comparing the solubility of salts from KSP value, they must have the same unit. If their unit is the same, then the salt with the lower KSP will be less soluble. Next, we'll look at ionic product. Ionic product quantifies the concentration of ions and anions with exactly the same expression as KSP that is found in the solution. So a good analogy to think about is that KSP is the seating capacity in the theater. So this is actually the seats that's available for the cation and anions to sit. That quantifies KSP. While ionic product is the number of patrons coming in to sit, whether they could be cation or anion. So if your number of patrons is more than the seating capacity, you will end up with precipitation because the cation and anion would now have to precipitate as a solid. If ionic product is equal to KSP, then the solution is saturated, which means in this case, all the seats in the theater is taken up by the cation and anion. Finally, if ionic product is less than KSP, then the solution is not saturated. Let's take a look at one of the examples. So in this example, we're studying the solubility product of calcium dihydrogen phosphate. So this is the equation for the dissolution of calcium dihydrogen phosphate, and you will get 2H2PO4 minus. Hence, the KSP expression is given as such. In the first question, we need to find out the number of moles of calcium dihydrogen phosphate that can dissolve in 100 cm cube of water. And we can do so by letting the concentration of Ca2 plus be X, and therefore your dihydrogen phosphate ion 2X. We substitute inside here, we can find the solubility of calcium dihydrogen phosphate in mole per dm cube. And we multiply by 0.1 dm cube, since it's 100 cm cube of water, to determine the number of moles of calcium dihydrogen phosphate that dissolves in 100 cm cube of water. And in this part of the questions, we're looking at a mixture of calcium nitrate and sodium dihydrogen phosphate being added to form a mixture solution. So it is important to take note that dilution occurs and concentration of ions need to be recalculated in the mixture solution. So this is the 2 steps that's taken. And finally, we can apply the concept of the ionic product to exactly the same expression similar to that of your KSP. However, the concentration of Ca2 plus is the concentration of Ca2 plus found in the mixture solution, which will be this value, and the concentration of dihydrogen phosphate is the concentration that is found in the mixture solution, which is of this value. By calculating the ionic product, which is 4 times 10 to the power of -7, we know the value is significantly lower than the KSP value, hence no precipitation occurs.